So, and as Vias already mentioned, mitigation is a quite challenging and interesting topic in this field. I would like to welcome our next speaker, which is Michael. So Michael, if you would like to share your screen, and I will give a short introduction about you. So Michael is currently the leader of Radiation Effects and Analysis Group at the NASA Goddard Space Flight Center, which he joined in 2007. Throughout his career, he has been working in the Central Spaceflight projects to capture system-level radiation responses through analysis and ground-based testing of semiconductors for research into promising future technologies through the NASA Electronic Parts and Packaging Program. The primary goal of this work and research is to provide support for mission success through implementation of radiation hardness assurance, which we heard already from Vias in practice. And he is a member of the Institute of Electronical and Electronics Engineering, IEEE, and the Nuclear Plasma Science Society, NPSS. And with that, we are looking forward to Michael's presentation about radiation mitigation strategies.
Let me just start off by saying thank you so much, John, for inviting me to talk. It's really great to see all of these speakers coming together and sharing all of this great information about the discipline that we're within. What I'm hoping to do is build upon the talks that have already been given and maybe raise that level of abstraction to talk about radiation mitigation strategies that we employ. Okay, so for today, I wanted to talk about this radiation effects come from a practitioner's view. So like I'm saying, one level of abstraction up, where we're dealing with the radiation effects within our systems that need to provide a specific function for us. If it hasn't been impressed upon you already, radiation is not kind to AAA parts. On the right, I'm showing some pictures of bad things that can happen. And this is physical damage to devices. What I want to go through today are some typical mitigations and talk to some of the limitations that they also have in terms of how far they can get you in terms of assurance. So like I said, we're looking at this problem from a practitioner's view right to the system level for something like radiation. And so we have to employ mitigation. And with that mitigation, there are some limitations. Let me get back to controlling. All right, so if we're looking at a system, we can describe things like failures in time of any product or system as having different probabilities throughout its life. If we look at this bathtub curve, which is typically called, there are 3 different regions. You can see early on, there's infant mortality. During the useful life of a device, there's this intrinsic failure rate that will always be there. And towards the end of its life, we see what is called like wear out. So if I put this in more of layman's terms, we are all making pancakes. The first pancakes that come off the griddle are burnt or not cooked correctly. Then we get into a rhythm and we're making great pancakes. But as time goes on, those pancakes cool off and they lose their efficacy for the people that want to eat them. If we lay radiation effects on top of that bathtub curve, we can see that dose shows up as wear out mechanisms. These are cumulative damage that happen over the course of your mission's life. And single events show up as random failures in time. These are instantaneous. One particle with sufficient energy in the right location is going to cause that effect. And so really you're dealing with a twofold problem when you're trying to mitigate radiation effects. Our job is to delay that wear out or dose impact to the systems that we want to fly. And for single event effects, we're really trying to push down or make acceptable the random failures in time to meet our availability and reliability needs for a given mission. So if you were a high risk, small sat, something like that, you may be willing to deal with very high probabilities of failure. And you might not have to do as much work to suppress the single event response. And you may not be up there long enough to even worry about the dose response to begin with. This was kind of the line of questioning that we were talking about just moments ago. But if you're a high, if you're intolerant to risk in a high class mission, you may want to very well provide yourself with a lot of margin on that dose response, and you may want to work very hard to bring down the impacts from SEE. I know that this was covered with earlier talks, but I just wanted to remind everybody that there are different single event effect signatures in the different components, and they have different impacts or what I would call persistence and consequences. This chart was put together by Ray Ladbury, and I think it does a good job at describing you the state space of all of the different single event effects and where they fall notionally in these realms. And so you can see at the very top right, destructive SEE, the thing that we are most trying to avoid, can be catastrophic and are permanent effects. And so it's important for us to try through part selection to avoid having to deal with those problem sets because we know it could be costly. But there are going to be single event effects that we cannot choose parts to avoid completely, and so we are going to have to design for them. So it's important to understand that this is very different than the idea if we're able to implement a lot of margin and push off the cumulative effects to beyond our mission doses, then it really is single event effects that we are left to deal with. And so if I'm looking at data from a solid state recorder, you can see that background during the quiet times of galactic cosmic rays and trapped protons, just error counts that are normal run of the mill. But we also have solar particle events that can cause large deviations. Here you can see the counts going up orders of magnitude for different S-class flares. This is a great plot showing some of the variability of an environment and our electronics actually responding to it. But this dynamic environment conditions that exist mean that our intrinsic failure rate is going to change temporally throughout our mission and makes our challenge that much harder. So if I look at that basic bathtub curve again, and I move it a little bit more towards reality, what you know is that we're going to have periods of varied dose rate and therefore also varied SEE likelihoods for different environment conditions. They are not always going to be in lockstep with one another, but you can see this becomes a very complicated problem very quickly. So this is why we deal with robust systems and a lot of mitigation where we deem it necessary. I'll go through some common examples now. Things that I ordered in terms of what you hear from folks who have just entered the realm of thinking about radiation effects. And so one of the first things you hear people say is like, well, can't we just shield those effects out? Well, shielding helps a lot. Don't get me wrong. A little bit of shielding goes a long way, especially in terms of the cumulative effects. On the left, I'm showing a dose depth curve. This is basically taking all of the environment's contributors, passing them through a amount of shielding. And so on the X ordinate, you are seeing shielding depth. And on the Y ordinate, you are seeing the total ionizing dose that's accrued. Really what you should take away from this is that once you get to a certain level of shielding, you've really gotten to a state of diminishing returns. For spaceflight, that means adding more and more mass, which is more and more of a launch cost. There gets to be a point where adding more mass is just adding more cost and not really changing the radiation response. Some of this is because and driven by the Bremsstrahlung radiation, and possibly this was covered earlier today. So a little bit of shielding goes a long way there. For single event effects, shielding does have a significant impact on the lower energy contribution from the environment and can change a lot of things that are caused by the proton environment that really dominates your error rates that you're going to see on orbit. But what shielding does not do is it does not change the galactic cosmic ray rates very strongly. So simply put, whenever you're thinking about single event effects that are going to happen within your build, this is another case in point where you need to avoid those destructive effects because there is an inherent background from the galactic cosmic rays that will always be a threat for those destructive effects. You can't shield them out. So again, shielding goes a long way, but it doesn't answer all of our problems. Next thing people suggest is, well, I would like to employ redundant systems. And redundant systems can be very great for things that are known as single points of failure within your design. But what redundancy doesn't solve is common mode failures. And so if you think about it this way, if I have two entire spacecraft serving the same function and they are redundant, maybe they're in a constellation, a very small constellation, you are not going to change the dose that happens or the degradation that happens. Both of those two entirely separate satellites are going to fail from dose around the same degradation levels. What redundancy does do, however, is it may reduce the risk, even though it's not eliminating it, it may reduce the risk to your mission's success of some single event effects. And so here I'm showing that you can compress the risk of destructive SE, mitigated SE, and non-critical SE from the redundant systems if you're talking about availability. So if what we are left with is these single event effects that we couldn't avoid, these non-destructive effects that are going to be within our systems, we're going to have to do something about it. And one of the first tenets, or one of the most common practices, is error detection and correction. There's a wide range of ways to go about this. You can implement it in hardware or software. On the right, I'm showing in hardware typical error detection and correction sequence. So you would write the data, use EDAC calculation to create these check bits. And as you read the data, you're going to compare those check bits with your EDAC correction, and you will be able to read the data out, knowing that if anything has changed from your write cycle. You can do similar things in software as well. It gets a little bit more complicated, and what that means from a radiation perspective is when errors are injected, where they are injected in your system, and when they get realized to your system. All of this is really the trade space that you're trying to understand, and the error detection and correction scheme that works best for you is going to vary. If you think about the different codes, there's PCH, Reed-Solomon. There's also things that look like single error correct, double error detect. There's also double error correct and detection. But you have to decide what's going to work best for your system. And it's not always just those bit errors that happen in the memory cells themselves. How you employ memories and implement them in your system, and how you spread those EDAC code words can have an impact on the system's response. I'm showing here a talk from Ted Wilcox that was given at SEE Maple D over here in the States, where different implementations, same system, but when the EDAC code words were written, whether or not it was sequentially filled or interleaved among the different die of flash, the impact really was driven by the single event functional interrupts. So it's the interrupt to the die itself. And those two different implementations realized the single event functional interrupt much more readily whenever the EDAC was filled sequentially. And so when you're thinking about mitigation, error detection, and correction, you also have to think about a level of abstraction of what you're going to have to deal with in your system and what works for you. In terms of architecture, if you are looking for other mitigations that are quite typical, you might find some publications and reference information on things like triple mode redundancy. This is where we use redundancy to vote and mask SEE. This is frequently used in FPGA projects of combinatorial logic. You can implement triple mode redundancy at the local level, at the block level, or even at a global level. It's all trades that are going to have different impacts for your system. But at a very basic level, what you are saying is if A, B, and C do not agree, use the two that agree and vote that state out so that you know you have a good known state. There's also cold sparing, where you may have two redundant cards of a system, one that is unpowered and can replace a faulty system. You are going to have to insert circuitry in terms of switching between those two redundant systems in order to make this work. So you're adding complexity. Both of those spare systems are going to accrue ghosts, and you need to keep that in mind. If it's non-volatile memory, it will still be accruing error even when it's off. And so you need to know that you're coming out of that state in a known state. But basically you're saying, if A fails, I can switch to B and continue my operation. Another architectural mitigation example is something like a watchdog timer. This is added circuitry that is watching over a process or a chip, and it's a feedback loop letting you say, something's not operating normally. I need to go through a power cycle, or I need to refresh a state so that I'm back to a known state so that I can reliably provide that process and give output. So these are some basic examples that show up a lot in our designs. There are, of course, more, but these were some of the most popular that I wanted to share with you all. It's also important to know that there can be operational mitigations, right? There's going to be, whether it's environment driven, availability driven, where you are on orbit and what's going on in the environment can drive different concerns and put your mitigation to the test at different times. And so you may decide that from an environment, whether you're passing through the SAA or there's flares happening on the sun, that you go into a safe mode where you are powering down some of the SCE's devices that are most susceptible, or maybe availability driven, where you don't have time from a ground intervention standpoint to reset. So you are going to schedule your power cycles, knowing that you're returning to a known state before an important measurement or returning to a known state before important communications. You can also implement this to happen autonomously, where you're not waiting for ground intervention and you're able to know that at some cadence you are going to be in a known state. And this helps a lot with anomaly resolution. It can also be just product driven. If your science data is coverage of the Earth, maybe you need to have a constellation or swarm where loss of spacecraft is okay, but you are meeting your reliability needs from strength in numbers standpoint. We see this regularly. You've seen this in the other talks. There's a lot of errors that show up in the South Atlantic anomaly, and when your orbit is passing through the radiation belts, you're going to be in harsher environmental conditions. But I want to pause and back up and put to the attendees here that it's really on you from a practitioner standpoint to decide if you need mitigation at all. And so what we can do is we can employ the practice of single event effect criticality analysis to understand if the impacts from radiation, especially SEE, even mean anything to your system. So we start with that severity assessment. What's the technology you're flying? What's the environment you're going into? And what's your concept of operations? We look at the application's architecture with the inherent mitigation, and we decide whether or not errors are something that we can function through, whether we are vulnerable to them, or whether or not they are critical and could impact our reliability. From there, we decide if the rates or accumulation of those errors are acceptable, and we can decide whether or not adding mitigation is useful and or cost effective. And we can then make the decision or the trade of whether or not we need to remove those components or remove a specific function or state that those components are going to be in from our design. And once we've met the functional requirement, we can then carry the anticipated error collection and the impact to higher levels, things like contingency, worst case analysis. And as long as we're communicating from a radiation perspective of what we anticipate, we don't need them to be classified as anomalies. We can understand if this, then do that. And that's really important and is becoming ever present in our job. We are not able to completely mitigate it away, and we are not completely able to part select all radiation hardened parts. And so susceptibilities are going to be within our designs, and we're going to have to be able to trace them back so that we understand what's going on, so that our systems can improve. Yeah, so my parting thoughts is that every form of radiation mitigation comes with a cost, whether that's your system's performance, whether it's increasing the mass, whether it's power consumption, or adding complexity. All of those costs are up to you to decide whether or not they are worth it. And our best practices are to know your environment, do the work to model the environment to the best of your ability so that you understand the variations and the extremes. You want to take into account the shielding that you have with your calculations, your rate calculations, and your dose, and you want to avoid over engineering a solution. It's important to note that good electrical engineering practices pay huge dividends on radiation susceptibilities. Things like margins, deratings, attention to signal integrity can already filter things like transients or help you ignore low-level local impacts to devices. When possible, it's great to verify that your mitigation actually does the job that you intended. So testing with and without mitigation is a really important practice from a radiation effects engineer's perspective. And you want to anticipate the need for when you can't avoid things like a power cycle or a refresh to a system. And that way you know you can get back to operation whenever you're on orbit. So again, thank you so much for having me, and I really am standing on the shoulders of everyone else's presentations here. I hope this was useful information for everyone to digest and leads to questions whenever you're procuring subsystems from folks or looking into cards with your colleagues. Thank you so much.
Thank you very much, Michael. Very good and nice presentation about mitigation strategies.